Going to have another look at inverse functions. We saw this back in, I think it was term 1. So we know that if there's a one-to-one relationship between two sets, then both the relation and its inverse relation will be functions. And in that case, we call the inverse relation an inverse function rather than inverse relation. Now, a function can either be one-to-one or many-to-one. Now, if it is one-to-one, then the composite function, so when we substitute the inverse into the function or the other way around, we should always get the answer x, because the inverses cancel each other out, if you like. How do we end up testing for them? The easiest way was visually. If it satisfied the horizontal line test, then we knew it had an inverse function. The other way is swapping the x and the y's around, and then the answer that you get, if it's unique, the inverse function of an odd function will also end up being an odd function. However, even functions will not have inverse functions, because even functions have symmetry in the y-axis, so that way it will always fail the horizontal line test. So domain and range. Because we're swapping the x and y's around, if AB is on the original function, then BA should be on the inverse function. So therefore, the domain of the original function becomes the range of the inverse function, and vice versa. So the range of the original function becomes the domain of the inverse function. Alright, let's look at some examples. We'll start with a function we've seen before, our exponential function. There's our e to the power of x. Its domain is all real x, and its range is y is greater than 0. Now, its inverse, so swap the x and the y's around, make y the subject, we get the log function. Or in this case, it would be the natural log. And we've seen that one before. Its domain does turn out to be x is greater than 0, and its range does turn out to be all real y. If I draw it, they should be reflections of each other in the line y equal x. And so there's our log curve. Not a lot of functions have inverse functions because of that problem with the horizontal line test. So sometimes we have to restrict the domain so we get a piece of the curve that we can turn into an inverse. So when we restrict it, what we try and do is we're going to get a piece of that picture that is continually increasing or continually decreasing. So it never turns around and comes back. Because as soon as it turns around, it's going to fail the horizontal line test. Let's look at the parabola, classic parabola. It of course fails the horizontal line test. Its domain is all real x, its range is greater than or equal to 0. But no good, we can't find an inverse. So we just want a piece of this parabola which is either continually increasing or continually decreasing. And we've got a couple of choices we could make here. We tend to go with the positives if we can. And 0 is also a good one to include if we can. This one, the logical one to pick, would be x is greater than or equal to 0. If we just look at that piece of the parabola, it's always going up. So that's going to become our restricted domain, and the range doesn't change. We still get the complete range with that piece of the parabola. So y is greater than or equal to 0. Swap the x and the y's around, and we get y is equal to x to the power of a half. Its domain will be x is greater than or equal to 0. Its range will be y is greater than or equal to 0. Now, whilst it's not obvious, because they were both greater than or equal to 0, what has actually happened is the domain and range have swapped around. If we draw it, that's where we get the top half of the parabola, because we're only inverting that piece of the parabola. So y equals x to the power of a half is the top half of that curve. The bottom half would have been if we picked the other one, and we would have got negative the square root of x, or negative x to the power of a half. Here's one from an HSC a couple of years ago. They gave us this graph, e to the power of minus x squared, which is that classic bell shape type of curve. They told us it has 2 points of inflection. Now, we haven't really looked too much about that with our calculus yet, but an inflection point is basically where the curve changes concavity. So it's where it goes from going concave down, or an upside down like the upside down parabola, to going to concave up, so the parabola we used to see. They want us to find the x coordinates of those points. Now again, something we haven't seen yet, but it turns out that when the second derivative, so differentiate 2 times, when that equals 0, that's the possibilities we look for with inflection points. So in this question, when they did it, that would have been the first thing they would have done. They would have said, okay, let's find when the second derivative is equal to 0. So we would have had to differentiate our exponential curve, and we get minus 2x e to the minus x squared. Well, that's just the first derivative. Do it again, but we're going to have to use a product rule. Write down the first, diff the second, plus write down the second, diff the first, and we end up with the second derivative. So to find these possibilities, we would solve when that is equal to 0. We end up with x is equal to plus or minus 1 on root 2. Now what we'll find when we start looking at this sort of curve sketching is, once we find them, we need to check whether they're inflection points. But in this question we don't, because they told us it has 2 points of inflection, and we've found only 2 possibilities. Therefore they must be the inflection points. We don't need to actually check. It then asks us, explain why the domain must be restricted to have an inverse. Because our graph that they've given us, it won't satisfy the horizontal line test. That's basically what they're looking for, that sort of thing. Now I put in the technical terms, I used the one-to-one idea. So well, we know it had to be a one-to-one function in order to have an inverse. And then I explained what that was. I said, well look, every value in the domain has to give a unique value in the range. So maybe I went overboard, but I reckon the key thing they were looking for is that idea of it had to be one-to-one, and the one we've got is not one-to-one. Find a formula for the inverse, and they've asked us to restrict it to the positives for this one. If it's just x is greater than or equal to 0. It's alright. We'll swap the x and the y's round. So x is e to the minus y squared. Now we go through the process of making y the subject. Now y equals plus or minus the square root of log 1 on x would give us not the inverse function, because remember we've restricted our domain, so we need to match it. We want the one where y is greater than or equal to 0, because that was the domain of the original one that we restricted it to. So which one of these would give us y's that are greater than 0? Well, the positive square root would give us y's are greater than 0. So our one will be the positive square root of the log of 1 on x. State the domain then. Well, the range of the original function will become the domain of the inverse function, and looking back at that graph, the range of the original function was y is in between 0 and 1, but not including the 0. Therefore, that becomes the domain of our new graph. They ask, okay, go and draw a picture. But you would have ended up something like that when you reflected it in y is equal to x. So basically it's the same picture, but it's now on its side, and just a piece that we were looking for. So that gives you an idea of the sort of thing they've asked in the past for the HSC. Okay, so let's play with 17A.